there are two basic languages, units of language: phonemes and morphemes. Phonemes refer to the smallest segment of speech that has a particular sound, and by virtue of that fact can change the meaning of a word. So if you loosen your vowels, a lot of the time you'll notice it gives you a different word. If I say but, it's got 3 phonemes. You would have remembered them from how you learn the ABCs. B, I, T. If I say bid, the last phoneme is the only thing that changes. But the differences between but and bid, based on a tiny little sound, create massive changes in meaning. But is a small part of something. A bid is sort of a rivalrous gesture to be able to have something who can create the highest bid. Meaning-wise, they can change just from the smallest inflection of sound. A phoneme has that kind of power. Ma and da are phonemes. But for every phoneme, there is also a morpheme. A morpheme is the smallest segment of speech that has its own distinct meaning. It means something all by itself. So the examples I use here are full or less. If you take them as suffixes, something you put on the end of the word, they can change the meaning of a word entirely. If I give the word use as an example, use obviously refers to whether something can effect a valued change in the pursuit of a goal. So is it useful? Useful means that it does something valuable in terms of achieving a goal, whereas useless means that it affects no meaningful change. Changing one sector of that speech because that word or that morpheme has a meaning of its own changes the word entirely. Everything we use is a combination of phonemes and morphemes, basic units of language. Everything boils down to them, and it creates a rather interesting effect. Now, forgive me for a moment, I'm going to need to get a piece of paper to illustrate this to you. Okay, thank you very much for being patient, guys. Now, as you can tell here, I have got a very specific phrase that has one particular letter missing. The entire meaning of this word is contingent on a single phoneme that I'm going to put there. Many of you have already probably guessed what that letter might be, and your ability to actually make that determination is based on something called the phonemic restoration effect. Warren conducted a fascinating study in which he found that when he presented an audio clip to an audience, and in the course of one word, the commentator coughed, he found that, number one, participants found it very difficult to designate where the cough occurred, and number two, didn't even recognize the fact that he had missed sections of a word. They filled it in automatically. Why? Because they had an idea of where that word would go based on the sounds at the beginning and at the end. With this, you make a similar inference, although it could mean, quite frankly, a lot of different things. I could say, you should luck off. I could say, you should duck off. For goodness sake. I could say, you should buck off, in some respects. The whole point behind it is that we can actually reconstruct sentences simply by virtue of understanding some segments of it rather than in its entirety. The same thing applies in a word superiority effect. We often find that we can remember letters, distinct parts of sentences, by remembering a word. This was something that Reicher did in an experiment. Reicher gave a set of stimuli to her participants, and Reicher found that in these stimuli, if she gave you the word fork, for example, then gave you a gap and asked you to remember if a particular letter was included in that, participants would do better than if she gave a non-word, like R-F-O-K. She would find that when you had a distinct unit of meaning, you could actually remember each segment much better, rather than if you had a whole bunch of different distinct segments. That shows you how morphemes can actually become meaningful to us, because they create a better meaning. Now, that's extremely important because that tells us that these unique segments, these small properties of speech, are actually the building blocks of the much larger units. Now, if we go back to how we actually learn language from there, one of the things that I'd want you to consider when we look at language acquisition is that the whole point of language development is to essentially take these smaller units, combine them into meaningful words, which form the corpus of language, as it's termed by Goldstein, or the body of information, essentially. And that's, of course, our vocabulary and our grammar, how we actually combine words and what words we know at that point. Language structure is very, very interesting because it mirrors knowledge structure. If you think back, I think to 2 lectures ago, when we looked at how knowledge operates, I'm just going to draw it while I'm busy saying it, we said that knowledge operates according to nodes, but that not all nodes are equal. If you think back to the parallel distributed processing model, or the PDP model, Collins and Quallain made a very, very important notion that while everything is based on a hierarchical organization, not all units are equidistant or equal potentials for everything. So for example, if we go back to the understanding birds, we have a basic concept of birds, and then we have flight birds and non-flight birds. Flight birds, some names would come to mind much faster than others, for the simple reason that the more frequent ones that we'd hear, the more prototypical we have, would essentially be the ones that would come up first, while others would come up later. Words operate in exactly the same way. We find that some words come to mind much faster, while others would take much longer, because of course some words create immediate associations, while others have a longer back propagation, a stronger signal pushing them out of conscious awareness until they're really called upon. This gets illustrated very nicely in some of the experimental findings that we'll be looking at. And one of the best ones is a lexical decision task. As illustrated here, it involves reading a list of words and non-words as stimuli. So it would be a whole list of different words. Some would say badger, yellow, fire, and of course the non-words would include things like guffaw, washling, and all sorts of other neologisms that I could continue to make up. You can amuse yourself by making up your own in all of that. But what they found in this task is when participants were asked to determine if this is a word or not, participants tended to respond much faster when they could identify whether there was something was a word, but even more so when it was a familiar word. Seeing something like couch was an easy determination for them, whereas seeing something like anachronism wasn't. It's not a word we would commonly use, whereas couch is something we use almost every day. The point is that couch would fall over here, anachronism a little bit lower down the hierarchy. You would see a stronger connection and therefore a faster recall time, whereas you would get a stronger back propagation for words that are less common, and an even stronger back propagation for words that aren't words to begin with. Why that becomes important is that it tells us that the parallel distributed processing model influences how we understand language, how easily we can actually comprehend something. But the word frequency effect is what was at play in that first experiment. The tendency to recognize that a word that you see more frequently is one that you can actually make a decision about faster. But it also gets explicated by a lexical ambiguity task, in which they actually show you that words can have multiple possible meanings. And I know we've already touched on this at the outset of the lecture with context. However, there are 2 different types of lexical ambiguity, 2 different types of uncertain meanings in words. According to Goldstein, you get balanced meaning dominance, where 2 possibilities have almost equal weighting, and you get biased meaning dominance, where 2 meanings have actual different likelihoods. So to illustrate, if you look at the term bank, if I say I went to the bank, he would make the argument that these are a balanced dominant, because of the fact that bank could mean a financial institution or it could mean the side of a river. Both seem fairly likely and equally probable. However, if I say I'm going to wear a cast on my arm, it would suggest that it's a plaster of Paris medical appendage, rather than the fact that it would be a dramatic ensemble of people. It's unlikely I'd wear them on my arm. Why this is important is that context and the PDP model explain why we are so different, yet so alike. As much as parallel distributed processing actually explains why people think differently and why people act differently, it also tells us why we speak differently. We speak differently because things like the word frequency effect suggests to us that some linkages in our lexicon are much stronger than others, creating an individualized knowledge base and a very distinct way of speaking. But we don't really stop at words, at a lexicon. We go one step up, and of course we create sentences, phrases that actually have distinct meanings based on combinations of words. And as they argue, all sentences have two distinct properties that are crucial to us and are represented in the brain in vastly unique ways. Sentences are quite valuable to us in terms of language because they actually illustrate some of the fundamental properties of neuropsychology. Through the use of the neuropsychological method, or finding out more about a function based on its absence in a particular person's brain, we learn a great deal actually about how language operates. And this is a great illustration of that fact, based on the fact that it's really rooted in two of the most seminal case studies in all of neuropsychology, by Paul Broca and of course his colleague Wernicke. There are two types of properties in a sentence. First is semantics, the meanings of words and sentences. So, for example, if you look at definitions, that's what semantics are. What does this word actually mean? Semantics is important because it's implicated in regions of the temporal lobe, which is usually defined as Wernicke's area. What's really interesting is that when Wernicke's area is damaged, we lose our capacity for semantics. We develop something called receptive aphasia. And aphasia, as you see defined on the slide, refers to a loss of the capacity for speech even though we have intact vocal cords. So it's a neurological syndrome rather than a physical disorder. When we develop Wernicke's aphasia, we no longer are capable of using meaning. So as a result of that fact, we often find that someone will have incoherent, meaningless speech all of a sudden. They'll speak, in some respects, psychotically. For example, someone with Wernicke's aphasia would suggest to us that essentially the plant was wrong because its relationship to the horsehound was really arbitrary, and as a result the wall really was going to chip away. They can no longer effectively use semantics, the meaning of words, to convey anything, and so get trapped in incoherent, meaningless speech. One brain region is almost entirely implicated in how we understand meaning. There is, however, a separate pathway for syntax. Syntax refers to the rules by which we combine words into sentences. Essentially, it refers to grammar. There is a right way of speaking, something that Yoda from Star Wars fundamentally disregarded, and is why he's so distinctive. He would say, "The dark side you must not go to," or "Go to, you must not, the dark side." We find his speech intriguing by virtue of the fact that he ignores syntax almost entirely. Typical rules by which we combine words to make sense of them isn't incorporated in the way that he understands things. Why this becomes important is that when regions of the frontal lobe named Broca's area are damaged, or if we see a lesion there, we often find that as a result we develop expressive aphasia, which is a tendency to have labored, ungrammatical and slow speech. We'll often find that while someone is using the right words, they combine them in a very nonsensical manner. So, if we think of an example in this regard, while someone would say, typically, "I broke my Samsung phone," they would often find themselves saying, "Broke phone Samsung is did what I." They can no longer actually combine those words, even though they can comprehend the meaning quite adequately. Both represent a distinct neurological pathway that, if lost, takes away our capacity to participate intelligently in language. Now, where things really get important is how we understand each other, how we understand language, how these sentences become meaningful within a context. Now, given that we've looked at how we acquire language, how we represent language, how we express language, we now need to look at how we comprehend language, how we begin to understand it in order to truly and fully understand the whole field of psycholinguistics. When we look at understanding language, we must be aware of the fact that all sentences are parsed, put into unique phrases within a sentence. Sort of, if you think of parsing, I always think of a comma as a visual understanding of that, how you understand you're starting one phrase and ending another within a broader sentence. Now, based on the definitions of words and the rules for combining them, semantics and syntax respectively, we usually parse, we divide a sentence up. Now, of course, Goldstein goes into great detail around theories of this, But really what becomes important is not so much the syntax first approach, but rather the interactionist approach, which is quite a broad system of thinking that really has only a few essential elements that one really needs to pay attention to. The interactionist approach reminds us that we naturally make inferences. We extend our knowledge beyond what is actually given to us in a sentence. We make certain assumptions based on the context of what we've heard. And when we hear phrases, we tend to engage in top-down processing.